In this demonstration, you'll learn some tips on how to obtain a converged solution for a fluid flow simulation. I'll import a journal file that will read in the geometry containing multiple inlets. This script contains all the necessary settings required to solve the physics. In fact, you can see that your physics is up to date. After solving the physics, you will need to check whether or not your solution is converged. There are a number of ways to find out if convergence has been achieved. You can look in the Messages tab to see if the solution converged. If convergence has not been achieved, you will see a message stating that the solution update stopped before the specified convergence criteria were met. In the case of a converged solution, you will not see this message. You can also check for convergence in the Solution Monitors tab. Here you will see a plot of the residuals at each iteration. To gauge whether your solution is converging, you'd want to see the residuals for all the equations except turbulence, which are excluded from the convergence criteria check, drop below 1 times 10 to the negative 5. There will be cases where your solution does not converge. I'll run through some typical scenarios where convergence isn't obtained, and I'll provide you with some tips on how to achieve convergence. This case shows residuals decreasing slowly and not reaching the target convergence criteria of 1 times 10 to the negative 5 within 200 iterations, as stated in this warning message. I'll demonstrate 2 ways to obtain a converged solution in this situation. First, I'll increase the maximum number of iterations in the Solution Controls panel to 500. I'll update the solution and check the residual plots. This will result in a converged solution, and I can confirm this in the Transcript tab. You'll see that the solution converges in 266 iterations. Alternatively, we can accelerate the rate at which the solver converges toward the solution. I'll adjust the solution advancement exponent towards aggressive by entering a positive value between 0 and 3. A value like 1 often accelerates slow convergence. And I'll update the solution. Here you can see that it converges in only 72 iterations. Sometimes the solution does not converge for other reasons. In the Solution Monitors tab, I see that the residuals are oscillating, which may be due to physical and/or numerical reasons. In such cases, a more conservative value like negative 0.5 or negative 1 may improve stalled or oscillatory convergence. Now you can see smoother residuals with fewer oscillations. To understand where the problem lies, it's always a good idea to look at the solution where the maximum residuals are located. The transcript tells me where the maximum residuals are. I can create a point at one of those locations and inspect the solution in the vicinity of that point to check for potential issues. To create a point, I'll navigate to the Results task and go to Construction Geometry to add a point. I'll create a point using the coordinates of the maximum residuals, negative 18.92, 14.20, and 0.9615. Next, I'll create a plane anywhere in the XY direction to display the plots. I'll create a velocity vector plot and inspect the results where the maximum residual is located. I'll choose the location to be the plane that I just created and the variable to be velocity. I'll need to go back and remind myself where the location of the maximum residual lies. Right here. And I'll zoom into this location. Here you'll see a separation zone, which is likely to be unsteady. Unsteady flow cannot be captured with a steady simulation such as this, which is why the residuals do not converge. This concludes this demonstration of convergence tips for a fluid flow simulation.